Hello, let me explain today's assignment, which is on graph traversals and their applications. So we are given an undirected graph G with vertex at V and edge at E. Now some of the vertices of the graph are red, the remaining vertices are blue. We know that a depth first or breadth first traversal can be used to detect cycles in a graph, directed or undirected, in this case undirected graph. Now we talk about cycles of three different kinds. A cycle like 13, 11, 5, 15 back to 13, which consists only of red vertices, is called a red cycle. Likewise, if I consider a cycle like this, 0, 7, 10, 9, 12, 3, 0, this is a blue cycle. So a red cycle or a blue cycle is called a monochromatic cycle. Okay, chromatic is number, color, mono means 1. On the other hand, if I look at a cycle like this, 13, 15, 3, 0, 7, back to 13, this is a cycle which consists of both red vertices and blue vertices. Okay. These cycles are called non-monochromatic cycles. So in this assignment, your job is to find out whether a given graph with each vertex having a color red or blue contains a red cycle or a blue cycle or a non-monochromatic cycle, multicolor cycle. Okay. So, first of all, propose a user-defined data type in order to store a graph. If a graph has, for example, n vertices, so it is natural to number the vertices in the range 0, 1, 2 up to n minus 1. And the overall graph G that has n vertices, we will number the vertices 0, 1, 2, 3, 4, 5, 6, like this. Okay. Now what we will do, we will construct this red subgraph which I call GR. This graph has, I think, 17 vertices, whereas this has only 1, 2, 3, 4, 5, 6, 7 vertices. And they inherit some vertex numbers from the parent graph G. Likewise this. Okay. So, they cannot be numbered 0, 1, 2, 3, 4. They may be indexed like that. So, they should be, okay, if you say, call this vertex 0, then you should know that in the parent graph, it has number 2, 6, 2, 4, 6, so 0 means 2, 1 means 4, 2 means 6, 2 means 5, 3 means 6 and so on. So, your graph data structure should consist of several things. It should be an independent, self-sufficient quantity, storing all possible informations about a graph. First of all, you should have the number of vertices, let us call it n, in this case nr, nb, whatever. Also, each vertex has a color, so there should be an array of colors. For example, here it is blue, blue, red, something like that, maybe represented by B and R, two characters. And as I mentioned, the vertices have some numbers, which is not necessarily 0 to n minus 1. So in an array, you should remember these numbers. And finally, the edge set. You use adjacency list representation for each of the graphs. Okay. Not adjacency matrix, adjacency list. And there is no necessity for storing the neighbors in an adjacency list in the sorted order. They can be in any order. Doesn't really matter. Okay. Now, after defining this data type, you should go about reading data about your input graph G. Okay. So this is done by user inputs. So what happens is the user first proposes this n, the total number of vertices, and then n colors, B, G, B, G, G, B, something like that. Sorry, RB, RB, BR, BBR, something like that. Then the user specifies the edges, for example 0, 3, 0, 7, 5, 15, 6, 12, separated by a space, and when the user enters a -1 as the first vertex in an edge, this has to be considered as end of input. So using these user inputs, you prepare a graph storing all the information relevant for the rest of the assignment. Good. So the next question is, we will first try the simpler thing. Okay, that is finding monochromatic cycles, that is either red cycles or blue cycles. Okay. For that, I will call the total graph G, and that graph induced by the red vertices. So these, and all the edges that are incident on red vertices only. They comprise a graph, let us call GR. So you create a subroutine that, given the master graph G and a color, red or blue, will create a graph in the same format called GR for the red graph or the blue graph GB, and return this graph. So this red graph and blue graph will have exactly the same format as the original graph G. Okay. Now you run, let's say, a DFS traversal on GR to detect whether there are any cycles. Okay. These thick edges in the red graph, they correspond to the DFS edges. This. Maybe I start from 5 or maybe I start from 2 and I detect this. Then I can go nowhere because this is no longer a part of the red graph. Okay. Then I look at 4. Again, 4 does not have any neighbor in the red graph. So stop. 5. Maybe I can go to 15, 13, 11, and that completes the DFS traversal. It is not actually a DFS traversal, it's a DFS, multi-DFS traversal. And this multi-DFS traversal generates a multi-DFS tree or DFS tree, which we call. So this consists of the single vertex 2 to 6, 5, 15, 3, 11. So these edges are marked by bold. Okay. So your DFS function, in addition to detecting the cycles, should create or maintain a list of these DFS edges. Okay. For example, you can use a parent-based representation. 2 calls 6, so parent of 6 is 2. 2 does not have a parent, so parent of 2 may be -1, parent of 4 is -1, parent of 5 is -1, parent of 15 is 5, parent of 13 is 15, parent of 11 is 13. So in an array, you store this information and return that array because that will be needed later. Likewise, you run a DFS, multi-DFS on this blue graph and remember or record all the DFS edges. For example, here I have started from 7, 7, 10, 9, 12, 3, 0. I cannot proceed further. Come back, come back, come back. Again, I have a possibility of going to 14. Here it may be from 8 to 1, then 8 to 16. Whatever it is, so you store the DFS edges in a parent array. You can also use your original graph structure, but just for storing a tree, you possibly do not need to do so much. Okay. You simply store whose parent is whom. And if somebody does not have a parent, -1. Good. Fine. So, this is one. So, DFS for detecting cycles. So, you know when DFS detects a cycle, whenever a back edge is detected. For example, if I start from here, 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 and then I detect a back edge 11 to 5. Then I may proceed using the parent array 11 to 13, 13 to 15, 15 to 5 to print that cycle. Okay. So your DFS function is a recursive function whenever it detects a back edge, it prints the corresponding cycle 11, 3, 13, 15, 5, okay, following the parent array. Also, it should create and maintain the parent array and return it. Okay. In the last part, we will require these two arrays returned by these two calls on the two graphs, red graph and the blue graph. Now we turn our attention to the non-monochromatic cycles. So that is cycles containing both red and blue vertices. Okay. So for that matter, we take a subgraph of G, the original graph G, whose vertex set is the same as the vertex set of G, all this 0, 1, 2, 3 up to 16, and all the edges that are shown by bold here. So there are three types of bold edges. One, the DFS edges, forest edges, the DFS forest edges on the red graph. Two, the DFS forest edges on the blue graph. And three, all edges that connect a red vertex with a blue vertex, like this, and this. So let us call this graph GRB. And now, a result in graph theory, which we ask you to prove, says that this original graph G contains a non-monochromatic cycle if and only if the graph GRB that you prepared contains a cycle. Okay. One thing is clear, that if GRB, this new graph, contains a cycle, it has to be non-monochromatic, because by sending only the DFS edges, you cannot create a cycle among the red vertices or the blue vertices. So if there is a cycle, it has to be non-monochromatic. But the point is that I have discarded this edge, this edge, this edge, this edge, this edge, this edge. And the idea is that by discarding this edge, these edges, which are not part of the DFS forests, we are not losing anything. If G contains a non-monochromatic cycle, we can still detect it from this reduced graph structure. Okay. So, you prepare this graph GRB. From G, you know what vertices, what edges are connected by or adjacent to vertices of different colors. This is available from G. And your DFS functions return these DFS forest edges. From that, you generate this thing. And together, you generate that GRB. Again, run a DFS on this GRB and get all the back edges and corresponding cycles, if any. Fine. So that is the assignment in a nutshell. Let me just quickly browse through the different parts. So storage, define a data type, number of vertices, the colors, vertex numbers, and the adjacency list, representation of the edges. Read a graph, user input, print a graph, okay, in a fashion illustrated in the sample IU section. And then write a function, get color graph, that given G, the original graph, and the color red or blue will generate and return the graph GR or GB, then DFS traversal. So, as I mentioned, whenever a black edge is detected, the cycle causing this black edge is printed, and second, you maintain that parent array, return it. So, of course, for detecting cycles and for the functioning of the DFS traversal itself, you need two other arrays. One is the level array. So, if U recursively calls DFS on V, then the parent of V is U and the level of V is one more than the level of U. And of course, you need a visited array. Okay. So, your DFS traversal, instead of printing the vertices, It will print the cycles detected by back edges and maintain and create and maintain and return this parent array. The next part is create the GRB graph. So these are the forest edges for the red graph, forest edges of the blue graph, plus all these cross edges connecting red vertices with blue vertices. The vertices is the complete vertex set. Create this, and this is the claim: G contains a non-monochromatic cycle if and only if GRB contains a cycle, and any cycle in GRB must be non-monochromatic. Okay. So call read graph to get G, then print the graph. Get call graph, color graph with color equal to R and B to get GR and GB, and invoke the multi-DFS function once on GR, once on GB to print all the edges, all the cycles, red cycles and blue cycles, and as byproducts to get the red and blue forest edges. So using this information and anything you require, you create that GRB graph and eventually call multi-DFS on GRB. Okay. And this is a theoretical exercise. Don't submit, but try to prove this claim. G contains a non-monochromatic cycle if and only if GRB contains a cycle. Okay, so in short, this is the sample IO thing you can figure out. The first enters the number of vertices, the colors, and then the edges. 0 is connected to 5, 0 is connected to 7, 0 is connected to 9. Of course, this is an undirected graph, so 0 is connected to 9 means 9 is also connected to 0. I assume that it's the user's responsibility that no edges are repeatedly supplied. I think there is a mistake here. I think there is a serious mistake here. 05 and 50 are both printed. Okay, I will change this. Okay, the user enters either 05 or 50, not both. So this is a mistake. I will correct it. Okay, and then how to print a graph? Color, vertex number, followed by the neighbors. Okay, no need to keep these things sorted, although in this sample IO it is sorted. You do not need that. These are the red graphs: 0, 3, 4, 6, 7. This is no longer 0, 1, 2, 3, 4, 5, 6, and these are the neighbors with this new numbering. Blue graph. There are no red cycles in the graph. One blue cycle. The color is blue, 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 as you can see. And then you create that non-monochromatic graph GRB. This consists of these vertices and these edges, and here are the multicolor cycles: BBRB, RBR, BRRB, and so on. Okay, so that's it. You start working on it. We will soon upload a fact page, and don't get misled by this. In your final assignment, you will not have this mistake. 05 and 50 both do not appear. Whenever 05 appears, you add the edge 0, 5 and also 5, 0. Okay, so that's it. Continue. We will be online. So in case of any queries, call us and submit. Today's assignment is slightly big, particularly the constructors are a little bit involved. So possibly we will give time to 5:30, beyond 5:30, maybe up to 6. So let us see. So you start your work.